So let's talk about Riemann sums. Suppose a general partition of A and B is given, such as the one we see here. So we have the interval that begins at x equals A and ends at x equals B. And so we have that general partition. On top of that, we're going to make some choices regarding these special x's that we choose within each interval. So here we write it with the star, xk with an asterisk, and so we could choose a point in each of these subintervals of our partition. Well, the Riemann sum is then the width of each of these partitions times the function f, okay? So we're doing a Riemann sum of the function f times the function f evaluated at each of these points, okay? That this special point that we've chosen in each of the subintervals. Of course, the question now is, well, how do you know which point to choose? If we had chosen the left endpoint of each of the subintervals, so for example, here we chose the left endpoint of the interval x minus, of this interval that begins at x minus 2 and ends at x minus 1, okay? So this is the n minus first subinterval there. The nth subinterval is here, and we chose the right endpoint there. For the third subinterval, we chose the midpoint, and we also chose the midpoint for the second subinterval. For the first subinterval, we just we didn't choose it to be right or in the middle, it's sort of somewhere in between there. So we have a left general Riemann sum. Why is it general? Well, it's because we chose a general partition. And if instead of a general partition we chose a regular partition, then we would just call it a left Riemann sum, although that's not really, standard convention. So the left general Riemann sum is one where you're choosing the left endpoint. Okay, so for our kth interval, we would choose xk minus 1. So this is the kth interval. We would choose xk minus 1. That's the left endpoint. A right general Riemann sum is one where we choose the right endpoint. Okay, so if we wanted to do a right general Riemann sum, we would choose here, that point there, and that's what we would plug into the function and multiply by the width of the interval to get the area of a rectangle. A midpoint general Riemann sum is one that's right in between. Okay, so we would have chosen this middle point here, right in between these two. And we would do that for each, not just this kth one that I drew there, but so a left Riemann sum has all of them being chosen the left endpoint of the subintervals, a right Riemann sum, all of the right endpoints. Okay? And of course, this was a general partition. We could have also chosen a regular partition. So typically, Riemann sums we encounter will utilize regular partitions. And what are regular partitions? Each of the subintervals has an equal length. Okay? And in that case, if we partition this into n subintervals, we would have a length of subinterval equal to this. So all of them would have that. Here we had a sub k here to indicate the length of the kth one. We don't need that anymore because they all have the same length. And so a left Riemann sum would be one where we choose the left endpoint. And now we could actually get a formula for xk star, the special point that we choose to evaluate the function at that point in that subinterval. If we chose the right Riemann sum, we would have that formula for the special point, this with the asterisk. And midpoint, we would have this formula for the special point that we choose. And we would carry out the Riemann sum with this formula here, okay? So we sum through all of the n sub, we go through all of the n subintervals and take the width of each of these subintervals and multiply it by that height. And although here we left out the label general Riemann sum, again, I'll stress that that's really unconventional. Most people just call this a left Riemann sum when it has the general partition. And, you know, they don't really make this distinction between general and then no label at all, okay? But this is mainly what we'll encounter here, okay? Regular partitions with left, right, and midpoint Riemann sums chosen as you see. So let's take a closer look at the Riemann sum to get a better idea of what we were discussing. So what you see here is a Riemann sum with a general partition. So this is utilizing the general partition. It's a general because the lengths of the subintervals vary. Okay, so the first subinterval is not as long as, say, the second or third subinterval that you see here. And we just call it a Riemann sum because we choose any of the, any x value, so any point in the subinterval, to evaluate the function at. Okay? Now, keeping the general partition, but making it a left Riemann sum now, notice we're evaluating the function at the left endpoints of each of the subintervals there. And doing a right Riemann sum instead, we're evaluating the function at the right endpoints of all of these subintervals. We could also do a midpoint Riemann sum where we evaluate the function at the midpoint of each of the subintervals. And this is a general partition, and as I said, we're pretty much only going to use we're only going to use regular partitions so that all of the subintervals now, notice, have the same length, okay? So all the subintervals have the same length. We get just a good old-fashioned Riemann sum here where we just choose any point in the subinterval to evaluate the function. Left Riemann sum where we're evaluating the function at the left endpoint of each of the subintervals. Right Riemann sum where we evaluate the function at the right endpoint of each of the subintervals. Notice that the second subinterval from the left there actually has an area of pretty close to 0, and that's okay. Okay, so that could happen. So that's the right Riemann sum, and we also have the midpoint Riemann sum there where we choose the midpoint of each of these subintervals. So this Riemann sum approximates the net area. So you would evaluate the function at, if it was a midpoint, as we see now, at the midpoint, and multiply it. So evaluate the function there and multiply it by the width of each of, or length of the subinterval to get the area of each of the rectangles, and sum through the area of all the rectangles, and that gives you the net area. To get better approximation, we increase the number of subintervals. So there's 24, 32, 38. And notice, the more subintervals you utilize, the more accurate your approximation is for the net area. And if you take the limit as n goes to infinity, you don't just get an approximate sign there, but you get an equal sign. Okay, so as the limit as n goes to infinity, or that delta x goes to 0, the width of the length of each of these subintervals, then you actually get the net area in the limit. Okay, so that's the basic idea behind the Riemann sum. And here is the formula. And as a recap, we'll just be using regular partitions with each one having equal length. And the big question is, where do you choose to evaluate the function at? Left endpoint, right endpoint, or midpoint? Okay. And typical examples has one approximating the net area under a curve using this Riemann sum. Okay. Let's take a look at this example here. So let R be the region bounded by the graph of this function, 3 times square root of x, and the x-axis between x equals 4 and x equals 16. So we want to approximate this net area using 6 subintervals, and we'll do it using a left Riemann sum, we'll do it using a right Riemann sum, and we'll also do it using a midpoint. So dividing out this interval so that we get our partition into 6 subintervals of equal length has each subinterval being equal to 2 in length. And we also get these grid points where k is running from 0 to 6. And so the first grid point is 4, the beginning of the interval. And we increase by 2 to get to the next grid point, all the way till we get to the 6th, to the grid point x sub 6, and that's the right endpoint there. And now the big question is, which endpoint do we want? Where do we want to evaluate the function? So if we're going to choose the left endpoint, we have a formula for that. Where did we get that formula? Well, because we're using a regular partition, we have this nice formula for the left endpoints. I mean, that would simply be 4, 6, 8, and on, and stop at 14 there. Okay, those will be all of the left endpoints of these subintervals, and you could see that here. Okay, so we get 6 of those. And now this is the Riemann sum. And so we could write it out since it's a short sum up to 6. So here it is fully written out there instead of using the sigma notation. This is the special point that we're choosing. We're going to choose x1 star is 4, the left endpoint of the first subinterval, the left endpoint of the second subinterval. 8 is the left endpoint of the third interval, on and on and on. And now we evaluate the function at those chosen points. So 3 square root of 4, where did that come from? Well, the function is equal to 3 times the square root of x. And so we get this sum down here. Giving in the left Riemann sum there gives us an approximation of 105.876. So what you see here is precisely the left Riemann sum we just evaluated. Okay, here are the different subintervals. That's the first one. The second subinterval, its area is approximately 14.697. The fourth subinterval, its area is approximately 18.974. And just what to note here is that we're using the left endpoints of all of the subintervals and then summing all of the areas of these rectangles to approximate the net area under the curve 3 times square root of x from 4 to 16. Okay, so what if we decided to do a right Riemann sum? Well, now we're going to choose the right endpoints of each of these subintervals, and here we just use this formula for the right endpoints of the subintervals when we have a regular partition. And we'll get that these are the right endpoints, 6, 8, 10, all the way up through, increasing in 2 up to increasing by a value of 2 units up to the point 16. Okay, and here's our Riemann sum. We're evaluating at the right endpoints now as opposed to the left endpoints. We're evaluating at the right, so we get 6, 8 instead of, say, 4 and 6 there for the first two. And we evaluate the function there and carry out the sum, and we get approximately a 117 there for the net area. And what you're seeing there is the right Riemann sum, okay? And so these are the different subintervals and the area of each of these rectangles. And let's compare that to the left Riemann sum. So that's the left Riemann sum. Notice we're choosing the left endpoint. The right Riemann sum, we're choosing the right endpoint of each of the subintervals. And you could see that choosing the right endpoints here gives us an overestimate, but that's not a general rule. That only occurred because this function is increasing, okay? But we can't make assumptions like that, so making very general statements that this is an overestimate or an underestimate, that is not too useful, because we could have functions that increase on some intervals but decrease on other ones, and so I wouldn't suggest trying to look for a very broad statement there. But it does occur here because the function is increasing. Had it been decreasing, we would get the reverse relation. We would find that the right sum would be a underestimate, while the left one would be overestimate. And if it was increasing and decreasing, well, we can't really say anything about that. Okay, so we looked at the left Riemann sum for this, and we looked at the right Riemann sum of this problem. Well, what about the midpoint Riemann sum? Here we're going to choose the midpoint, and we have a formula for that. It was written up here for choosing the midpoint. But you could tell what the midpoints are for these. There are a few subintervals, just 6 of them. So we could see that if the left endpoint was 4 and the right endpoint was 6, well, what's going to be the midpoint? For the first subinterval, it's going to be 5, okay? Or you could just use this formula where k is running from a 0 up to, or 1 up to n there for this formula, okay? So here we should have that k is going from 1 up to n, the number of partitions. Okay. So say using that formula for the first one, we would have k equals 1. That's 1 minus a half. That's a half times 2. Well, that's just 1. So 4 plus 1, we get 5. Okay. Perfect. And we could do the same thing now where we're evaluating at the midpoints. Okay. Notice these are all the midpoints. And we carry out that sum, and we get 112.062.